Good day, everyone. I am Vikas Kumar, Assistant Professor, IIMT College of Science and Technology, Greater Noida. Today, I am delivering a lecture on order relation and posets. Uh, the contents for this lecture are order relation, properties of relation, partial order relation, posets, some examples, and a few applications of order relations. Ordering refers to the arrangement or organization of objects and elements on based of specific criteria or rule which these objects or elements exhibits. The ordering is useful for comparison of objects, classification of elements, sequencing of events, or sequencing of tasks. Optimization of optimization means doing tasks in such a sequence that optimized result obtained, and in data analysis and in logical reasoning. So we notice that ordering is very useful in wide context. It has concern in various fields. The properties of relation, the some essential and useful properties of relations are the reflexivity, symmetry, transitivity, antisymmetry, asymmetry, reflexivity, and totality. That is connexity. Now we will show these properties. The type by these properties, the type of relations we can discuss, or we are using, we will be use only useful uh, relations which are useful for this session. There are different type of order relations, including partial order relations and total order relations. Partial order relations are those relations which relation exhibits reflexive, antisymmetric, and transitive property. In the last slide, we have discussed 7, or there may be more properties, 7 properties which relation exhibits. So if a relation, a order relation exhibits 3 properties or fulfill 3 properties, that is reflexive, antisymmetric, and transitive, then this relation is said to be a partial order relation. Moreover, a total order relation is also given here. A total order relation is a partial order relation but has a additional property that each two elements are comparable. So partial order relation and total order relation have some similarities. But In this session, we will further study the partial order relations. So, partial order relation, this is the definition part. We are defining a partial order relation, a relation which is denoted by less than or equal to is said to be partial order relation if following three property, which is reflexivity, antisymmetry, transitivity, is fulfilled. We have earlier told this thing in last slide, but we will explain what the reflexivity means, what is the antisymmetry means, and what is the transitivity means in this slide. So it is clear a partial order relation is a relation between the objects which exhibits three properties, which is reflexive, antisymmetric, and transitivity. Reflexivity means for each elements in a set P, A is less than or equal to A. Here, this less than or equal to means a relation. Okay, so A is related to A. So the reflexivity means every element related to itself. Now, the meaning of antisymmetry, the statement is if A related to B and B also related to A, then A must be equal to A. This is the antisymmetry property. So, if this condition fulfilled, we will say antisymmetry property is fulfilled. Means if A related to B and B related to A, then A is equal to B. Now, the transitivity means if some element A related to B and some other element B related to A element C, then the first element A is related to the last element C. This is the transitivity. So, these three properties are explained. Now, we are going to define a poset. So, up to now, we have noticed there is a set P from which objects we are taking, and there is a relation or order relation which is denoted by less than or equal to, and this relation is partial order relation if it fulfill three properties, which is reflexive, antisymmetric, and transitive. So now we are defining partial order set. Definition: a partial order set is a set P equipped with binary relation less than or equal to which is partial order relation is called poset. That means a set is said to be poset if the relation defined over this set is partial order relation, or it can be defined as if the element of the set P fulfill three properties: reflexivity, antisymmetry, and transitivity, then P is said to be the poset. Partial ordering, here is an example which is representing the ordering and partial ordering between four sets, set A, B, C, and D. Set A comprising two elements, B comprising three, and the set C comprising four elements, namely 1, 2, 3, and 4. And more, we have one more set D, which is 5 and 6. By seeing these four sets, we notice that A is subset of B and B is subset of C. And A is also subset of C. But there is no comparison between set A and D, except the number of elements in A are 2 and the number of elements in set D are 2. But these are not, these two sets or first set A, B, C are not related to set D. So, if we considering a relationship of is a subset of, then we got following relationship. That is, A is subset of A is subset of B, A is subset of C, B is subset of B, B is subset of C, C is subset of C, and D is subset of C. We notice by these blue relations that the reflexive property holds because every element or every set is related to itself. Moreover, if we see A is less than A is related to C, that is A is subset of C, then it exhibits the transitive property. Since A is subset of B and B is subset of C, that means A is subset of C. Moreover, we can see by the set simple operations A is subset of C. So transitivity property also holds. If we talk about antisymmetry, antisymmetry property holds because there is no element which is less than first element or which is related to first element, and also it is related to second element or both element related to each other, then these two elements must be equal. So there is no such case which is contradicting this property. So we say this collection of set A, B, C, and D exhibit partial ordering among the sets. So we notice by the above conclusion that partially ordered set are the mathematical structure used to represent ordering between the elements of sets. And these elements can be the sets of sets. Like in the last slide, we have uh, uh, taken the sets itself as an object of a set. The ordering is partial since some elements do not have relationship. Means we have noticed that D related to itself, but D is not related to A, B, and C, any of these. Even though the collection of set A, B, C, D is exhibiting a ordering. This is partial ordering. We have taken more example of Posets or partial ordering. There are three examples the set of natural numbers with the operation of less than or equal to is a poset. That means this relation of less than or equal to is a partial ordering over the set of natural numbers. These subsets of a set with set inclusion relation is again a poset. The set of positive divisors of a number n with the operation or with the relation of divides is also posets. I am including these three examples of posets in this lecture because we are taking care of time duration. The first example, that is the set of natural numbers with a operation is less than or equal to is poset. It is explained in the next slide. Since every element, that is 1, 2, 3, 4, are less than or equal to itself. So reflexivity property holds because every element related to itself. Moreover, we notice if A related to B and B related to A, then A is equal to B is the antisymmetry property. We notice in this case, there is no number between two elements which fulfill a condition A is less than or equal to B and B is less than equal to A, then it is obvious A must be equal to B. Moreover, if we take any three numbers A, B, C, and I am saying first one is less than or equal to second and second one is less than or equal to third one, then it is obvious the first one is less than or equal to third one. So transitivity is also fulfilled. So we can say this relation of less than and equal to is a partial order relation, and this set n with this ordering is a poset. Moreover, a collection of subsets of a set with set inclusion is a poset. I am explaining this is in short that we know that by the simple operations of set, every cell, every element or every set is a subset of itself. Here it is written every set is subset of itself. So reflexive property is fulfilled. Moreover, by the set equality, we know that if A is subset of B and B is subset of A, then these two sets AB must be equal. Transitivity property again hold since A is subset of B and B is subset of C, then it is obvious A is subset of C since C is superset of these both sets. So we notice that reflexivity, antisymmetry, and transitivity is fulfilled by the relation of set inclusion for this collection of subsets. So we can say this collection of subsets is a poset and this set inclusion is a partial order relation. Moreover, the third example, we are taking the set of positive integral divisors of a number n, and we are describing this set with a relation of divide. So this relation, if it is reflexive, transitive, and antisymmetric, then we will say this relation of divide is partial order relation, and this set of positive integral divisors of n with this relation is poset. Since we know every number divides itself, so we can say reflexivity property hold, transitivity property also hold because D divides E and E divides F. Then it is obvious D divides the largest number F. Antisymmetry holds since there are there are cases when we say D divides E and E also divides D. That means these two numbers are equal. So these three properties are fulfilled. So this set of positive integral divisors of n is a poset with the relation of divides. The application of these ordering and posets are in various branches. Uh, Now we have included a few here mathematics. This has applications in set theory, order theory, and lattice theory. Moreover, in computer science, in topological sorting, data structure, and decision making. Moreover, we have taken physics and engineering in circuit design and quantum mechanics. Posets and order theory has applications. If we talk about economics and social sciences, then in preference, relation, social choice theory, ranking system, posets and order relations have applications. So we noticed that, or we discussed in this lecture, partial order relations are useful and how these are useful and how these are rise to posets. That's all for this lecture. Thank you very much.